Good afternoon, everybody. I am Sridhar Rao, is on the Zoom online teaching. Let us have some properties of linearly independent and dependent sets. As I stated earlier, that a set containing a null vector is linearly dependent. So let us have those properties and we shall have it in the form of a theorem. Let V be a vector space over a field F, then the set of vectors of V containing the null vector is linearly dependent. Second property is the set consisting of a single vector alpha of V is linearly independent if and only if alpha not equal to 0 vector. And the third property is every non-empty subset of a linearly independent set of vectors of V is linearly independent. And fourth, any superset of linearly dependent set is linearly dependent. While giving the proof, I shall explain each and every property in a lucid manner. The first one, the set of vectors of V containing the null vector is linearly dependent. The meaning of this is, if you have a set of vectors of a finite vector space V, and if one of the vectors in the subset S is a null vector or a 0 vector, if one of the vectors is a null vector or a 0 vector, then that set S is clearly linearly dependent. The proof is as follows. Let S be alpha 1, alpha 2 to alpha n, be a set of vectors of V. Remember here, alpha 1, alpha 2 to alpha n, they are the elements of the vector space V, and S is a subset of V here. Suppose S contains a 0 vector. Suppose S contains 0 vector. We don't know whether alpha 1 is 0, alpha 2 is maybe 0, alpha 3 may be 0, or alpha n may be 0. That we do not know. Let us assume that. Suppose alpha 1 is 0. Let alpha 1 be 0. If alpha 1 is 0, how could you write alpha 1? You could write alpha 1 as 1 into alpha 1 plus 0 into alpha 2 plus 0 into alpha 3 plus so on 0 into alpha n equals 0 vector. If once you simplify the left hand side, you will get alpha 1. So therefore alpha 1 equals 0 implies 1 into alpha 1 plus 0 into alpha 2 plus 0 into alpha n equals 0, because 1 into alpha 1 is alpha 1. That is equal to what? 0. From this, what you observe is, we have expressed alpha 1, alpha 2 to alpha n as the linear combinations. In other words, here 1, 0, 0, 0, they are all scalars. So 1 and 0, they are all scalars here. Therefore, it's a linear combination of alpha 1, alpha 2 to alpha n, which when equated to 0, does it imply that all the scalars are zeros here? No. Second scalar is 0, 0. Third scalar is 0. And the last scalar is 0, but the first scalar is different from 0. What is the first scalar there? So first scalar is, that is 1. First scalar is what? 1. So 1 is not 0 here. So it is the set of all linear combinations is 0, but there exists at least one scalar different from 0, then the set of vectors is linearly dependent. That is the definition of linearly dependence. So according to the definition of linearly dependence here, we have expressed alpha 1, alpha 2 to alpha n as the linear combination of finite number of vectors, and when we equated to 0 here, according to linearly dependence definition, all the scalars must be 0 for linearly independence. But for linearly dependence, there exists at least one scalar different from 0. Yes, it is clearly true here. It is quite clear from the first vector what we have, 1 into alpha 1. The first expression is 1 into alpha 1, where 1 is a scalar, 1 is not 0. Therefore, the set of vectors is linearly dependent. We express this in C1 alpha and C2 alpha to Cn alpha n is 0, in which all the Ci's are not 0 is valid here, because First scalar is not 0. If one scalar is not 0, what do you say about this? The set is linearly dependent. Therefore, a set containing a null vector is always linearly dependent. So it's quite obvious now. If you have a vector like 0, 0, 1, 2, 3, 4, 5, 6, that set is linearly dependent because it has a null vector 0, 0. So you can clearly identify whether it is linearly dependent or independent. Now, second one, the set consisting of single vector alpha of V is linearly independent if and only if alpha not equal to 0. If a set has only one vector, say alpha, then the set is linearly independent provided alpha not equal to 0. Converse is also true. That is, if alpha is not 0, then the set is linearly independent. If it is linearly independent, a set consisting of a single vector alpha, so it's a singleton set having alpha alone, that alpha not equal to 0. Converse is also true because of if and only if condition. Let us prove this. Let alpha, the set containing alpha, that is singleton set, it has only alpha. Let alpha be a set consisting of a single vector. What I have to prove here? Let alpha be linearly independent. That I have taken. It's a data or it is given. Let alpha be linearly independent. That is, set containing alpha is linearly independent. According to that result, as we cited above, what we have to prove is alpha not equal to 0. So we have to prove that alpha is not equal to 0. So what we have taken, the set consisting of single vector alpha is linearly independent. So it suffices to show that alpha not equal to 0. So alpha is different from 0. Now we shall go by contradictory method. So what the contradictory method we do employ here? Suppose alpha is 0. Suppose alpha is 0. What I have to prove actually alpha not equal to 0, but I go by contradictory method. Suppose alpha is 0, then arrive at a contradiction. At the end, I should arrive at a contradiction here. Suppose alpha is 0. Then the set alpha is a set consisting of null vector. So set alpha is consisting of a null vector because if alpha is 0, 0 implies it's a 0 vector, remember. Generally, we denote by O or 0. So because if it is two-dimensional, it is 0, 0. If it is three-dimensional, 0, 0, 0. Three-dimensional, four-dimensional like this, you'll have 4 components like that. So what we have is set alpha. It is a set consisting of a null vector. As we cited above in the first property, what we have, set consisting of a null vector is linearly dependent. So what we have here now, if alpha is 0, then the singleton set alpha is a set consisting of the null vector, and hence from first property, what you can say, set is linearly dependent. But what we have taken here, alpha is linearly independent. In the beginning, what we have taken, the set alpha is linearly independent. But what we have arrived at now, alpha is linearly dependent. This is a contradiction to our hypothesis. What's our hypothesis? It's linearly independent is our hypothesis, but we have arrived at a contradiction. So set alpha is linearly dependent because of our choice of alpha. What we have chosen alpha equals 0 vector. That is wrong. We have gone by wrong method here. What is that? Choosing alpha equal to 0. Therefore, alpha should not be 0. If we choose alpha equals 0, what happens? The set alpha consisting of a null vector that is linearly dependent. But what we have taken, let alpha be linearly independent that we have supposed. So therefore, this supposition alpha equals 0 is wrong. Then what it should be? So it contradicts alpha is linearly independent, hence alpha not equal to 0. The one half of that result is being proved now. What is the one half? Suppose it is linearly independent, then alpha is not equal to 0. Converse is there. What is the converse? Suppose alpha is not 0, what I have to prove? The set consisting of single vector alpha is linearly independent. Let us prove the converse now. Conversely, suppose alpha not equal to 0. Suppose alpha not equal to 0. Then what I have to prove is set is linearly independent. The set alpha is linearly independent. That I have to prove now. What I have taken now? Suppose alpha is not 0. Consider C into alpha equals 0, where C is a scalar belonging to the field F. Suppose the C into alpha is 0. This implies C is 0 or alpha is 0. This is one of the properties that we have discussed earlier. Earlier we have this property of the vector space C into alpha equals 0 implies either C is 0 or alpha is 0. This is one of the properties that was proved earlier. But alpha is not 0. According to this, C into alpha is 0 implies C is 0 or alpha is 0. But here what we have taken, alpha is not 0. Because alpha is not 0, what it should be then? C should necessarily be 0. Therefore, C equal to 0. This implies C into alpha is 0, implies C equals 0. What is this definition? Something like linear independence definition. In the linear independence definition, C1 alpha 1 plus C2 alpha 2, but here we have only one vector alpha in this set. Therefore, you cannot take alpha 1, alpha 2, alpha 3, alpha 4 like that. So, C into alpha equals 0 implies scalar C is 0. This is definition of linear independence. We have only one alpha because the set here contains only one alpha. If the set contains alpha 1, alpha 2, alpha n, then we have to take the linear combination C1 alpha 1, C2 alpha 2, C3 alpha 3, so on. But here we are bound to take only one vector alpha because the set contains only one vector. Therefore, C into alpha equals 0 implies C equals 0. That is a scalar 0. That is, the set is linearly independent. This is the definition of linear independence. C into alpha equals 0 implies C equals 0. That is, every scalar is a 0. If the scalar is not 0, it is linearly dependent. But here scalar is necessarily 0. Therefore, the set alpha is linearly independent. Thus, what we have proved? We have proved that the set consisting of a single vector alpha of V is linearly independent if and only if the condition alpha not equal to 0 is valid. Next, we'll prove the third result. What is that third result? Every non-empty subset of a linearly independent set of vectors of V is linearly independent. The meaning of this is, if you have a linearly independent set, some set of vectors, they are linearly independent. Take the subset of that linearly independent set. Take the subset of that linearly independent set, then that set is linearly independent. This was also cited as an example. What is that example is 100010. Yes, 1000100001 is linearly independent in V3 of R. Some leave out some one vector there. For example, 100 or 001. Yes, you remove 001 from this set. Then obviously another set S1, you can call that as S1, having 100, 010 alone. That is these two vectors. That is obviously a subset of what? It's a subset of capital S. So therefore, what we have is, if you take these two and you will take C1 alpha 1 plus C2 alpha 2 equals 0, implies C1 is 0, C2 is 0. That is, that set is also linearly independent. In other words, any subset of linearly independent set is linearly independent. That is the meaning of that theorem, that result. So now we shall go to the proof of that. Let S, capital S, be linearly independent subset of V. We have taken S as a linearly independent. Now what we have to do, we have to take another set that is subset of this capital S. So let T, capital T, be a subset of S. What I have to prove now? T is linearly independent. I have to show that T is linearly independent. There are two possibilities. T may be an empty set or T may not be an empty set. Suppose T is an empty set, then it is linearly independent. This is because we have in the definition of linearly independence, we have a note there. That note may not be here. Okay, I shall go through that, whether that note is there or not. Yes. Here we have the null set phi is always taken as linearly independent set. Null set, that is any null set, is always a linearly independent set. This is for the sake of convenience, it is being accepted. So therefore, any null set or a set, empty set is always linearly independent set. So obviously, if T is a null set, then it is linearly independent according to that note. Quoting that note, you can say that that set is linearly independent. Next, suppose it is not a null set. Suppose T is not non-empty set. It is a non-void set. It is not a null set. Then what we have is there are two possibilities. S may be finite set or it may be an infinite set. S may contain finite number of elements or it may contain infinite number of elements. Suppose S has a finite subset of V. Suppose S is a finite set, that is, it has finite number of elements. What is S? Alpha 1, alpha 2 to alpha n. What is T? Alpha 1, alpha 2 to n, alpha n, provided here M should lie between what? 1 and n. Because otherwise it cannot be a subset. If it were to be a subset, M should be less than n, remember, or less than or equal to n, and then greater than or equal to 1. So it is a subset. Therefore, M is less than or equal to n here. Next, let C1, C2, Cm, they are the scalars belonging to the field F, and suppose the linear combination is 0, that is C1 alpha 1 plus C2 alpha 2 plus Cm alpha m is 0. What I have to prove is T is linearly independent. In order to prove that T is linearly independent, by the definition of linear independence, it is enough if we can show that all the scalars are zeros. What are the scalars? C1, C2, so on, Cm are 0. That I have to prove. If I prove that, obviously T is linearly independent, because in the definition of linearly independent, if the linear combination of alpha 1, alpha 2 to alpha m is 0, then each of the scalars must be 0. If one scalar is different from 0, then it is linearly dependent. If all the scalars are necessarily zeros, then T is linearly independent. So it is enough if I can prove that C1 is 0, C2 is 0, C3 is 0, C4 is 0, so on. Cm is also 0. That we shall establish further. Next, then C1 alpha 1, C2 alpha 2, so on, Cm alpha n, 0 into alpha n plus 1, 0 into alpha n is 0. Implies C1, C2, Cn is 0. Why? Why this happens? Because S is linearly independent. Because S is linearly independent here, their linear combination equal to 0 implies each of the scalars is 0, because S is linearly independent that I have taken in the beginning. So therefore, what is this one? C1, C2 to Cn alpha n. So I can write Cm alpha m as Cm alpha n plus 0 into something is 0. 0 into alpha n is 0. Therefore, it is nothing but Cm alpha m equals C1 alpha 1 plus C2 alpha 2 plus so on. Cm alpha m equals 0. So here each of the scalars is 0. Why each of the scalars is 0? Because S is linearly independent that you have taken in the beginning. Hence, C1, C2 to Cn, somewhere here you will get Cm in the middle. C1, C2, C3, C4, Cm plus 1, Cm plus 2, so on, Cn equals 0. But what is our aim? Our aim is to show that only C1, C2 to Cm are zeros. But we have here C1 equals C2, so on up to somewhere Cm here equal to 0. Therefore, T is linearly independent set. So what we have proved, if it is a finite set, if S is a finite set, then its subset T is also linearly independent because of S, which is linearly independent. Since S is linearly independent, the subset T of S is linearly independent if S is a finite subset of V. Then what is the other possibility? S may be an infinite set. So second possibility is that S be an infinite set. Then also what I have to prove? I have to prove that the subset T is linearly independent. If T is a finite subset of S, remember S is linearly independent and is also infinite set. Suppose T is a finite subset of S. An infinite set can have a finite set. An infinite set can have a finite set as a subset. So if T is a finite subset of S, then T is a finite subset of an infinitely linearly independent set. Yes, because it is finite from the first one, what we have proved. It is a finite subset. If S is linearly independent, T is also linearly independent, that we have proved here in the first one. So next, therefore T is linearly independent. If T is an infinite subset of S, then W be any finite subset of T. Note the difference there. W is a subset of T is a subset of S, W is finite subset, T is infinite subset. Then W is linearly independent because W is finite subset that we have proved there, as S is linearly independent. Hence, T is also linearly independent. This is something like chain because W is a subset of T is a subset of S. Note the logic there. Because it is a finite subset, it is linearly independent. Hence, the subset T is also linearly independent. Proof of the fourth one. What is the fourth one says? Any superset of a linearly dependent set is linearly dependent. What do you mean by superset? Superset is nothing but here. Suppose A is a subset of B, then B is called superset. A is a subset, B is a superset. Suppose capital A is a subset of B, then B is called superset and A is a subset. What I have to do? Superset of linearly dependent set is linearly dependent. That is the meaning of this. So let capital S equals alpha and alpha m be linearly dependent set, so that C1 alpha and C2 alpha to Cm alpha m is 0 implies not all the scalars are zeros. In other words, there exists at least one scalar different from 0, say Ci. Ci is somewhere here. Here we have Ci alpha I. C1 alpha 1, C2 alpha 2 plus so on, Ci alpha I plus so on, Cm alpha m equals 0. So there exists at least one scalar not equal to 0 because it is linearly dependent. Consider the superset. Superset is nothing but that contains this set capital S. Superset is nothing but it contains capital S. That is all the elements of S are in this superset. So it is alpha 1, alpha 2 to alpha m extra one element because it's a superset. It should have more elements than S. So extra one element, say alpha. So alpha 1, alpha 2 to alpha m alpha. Then what I have to prove is superset is also linearly dependent. In other words, I have to take the scalar linear combination of those vectors and I have to show that there exists at least one scalar different from 0. Next, then C1 alpha and C2 alpha to Ci alpha Cm alpha m plus C alpha, remember it is C alpha, not C alpha u, but it is C alpha equals 0. What I have to prove is there exists one Ci not equal to 0. I have to show that one Ci not equal to 0. Obviously, because here what is S? S is linearly independent. This implies C1 alpha and C2 alpha to Cm alpha m equals 0 implies at least one Ci is not 0 is mentioned here itself. That also holds for this because Ci is also here. Ci is also here. Therefore, there exists one Ci not equal to 0. Therefore, what do you say about this set, superset? Superset is linearly dependent. Remember, it should be dependent, not independent. So is not linearly independent. Okay, that is right because it is linearly dependent. So it is not linearly independent implies it is linearly dependent. So these properties are very important in view of the examination. These properties will be asked in the examination in due course. Next, let us have another theorem. So what the theorem states is, a set of non-zero vectors alpha 1, alpha 2 to alpha n of a vector space V of f is linearly dependent if and only if some one of these vectors, say alpha k, where k lying between 2 and n, is expressed as the linear combination of the preceding ones. The meaning of this is, we have some non-zero vectors alpha 1, alpha 2 to alpha n of a vector space V of f. If it were to be linearly dependent, ಒಮ್ಮೆ ಇದು linearly dependent ಆಗಬೇಕಾದ್ರೆ ಇವಿಷ್ಟು ವೆಕ್ಟರ್ ಅಲ್ಲಿ ಯಾವುದೋ ಒಂದು ವೆಕ್ಟರ್ ಸೇ ಆಲ್ಫಾ ಕೆ ಯಾವುದ್ರ ಮಧ್ಯೆ ಇರಬೇಕು, ಆಲ್ಫಾ 2 ಮತ್ತೆ ಆಲ್ಫಾ ಎನ್ ಮಧ್ಯೆ ಇರಬೇಕು, ವೇರ್ ಕೆ ಲೈಸ್ ಬಿಟ್ವೀನ್ 2 and n ಇದೆ. ಆದ್ರಿಂದ ಆಲ್ಫಾ ಕೆ ಅನ್ನೋದು ಆಲ್ಫಾ 2 ಮತ್ತೆ ಆಲ್ಫಾ ಎನ್ ಮಧ್ಯೆ ಇರುವ ಯಾವುದೋ ಒಂದು ವೆಕ್ಟರ್ ಅನ್ನ ಅದರ ಹಿಂದಿನ ವೆಕ್ಟರ್ ಅಲ್ಲಿ ಎಕ್ಸ್ಪ್ರೆಸ್ ಮಾಡಕ್ ಬರಬೇಕು ಲೀನಿಯರ್ ಕಾಂಬಿನೇಷನ್ ಅಲ್ಲಿ. ಅಂದ್ರೆ ಆಲ್ಫಾ ಕೆ ಇಂತ ಹಿಂದಿನ ವೆಕ್ಟರ್, ಆಲ್ಫಾ ಕೆ ಇಂತ ಹಿಂದಿನ ವೆಕ್ಟರ್ ಅಂದ್ರೆ ಆಲ್ಫಾ ಕೆ ಮೈನಸ್ 1, ಆಲ್ಫಾ ಕೆ ಮೈನಸ್ 2, ಸೊ ಆನ್ ಆಲ್ಫಾ 2, ಆಮೇಲೆ ಆಲ್ಫಾ 1, ಇದರಲ್ಲಿ ಆಲ್ಫಾ ಕೆ ಮತ್ತು ಇ ಅನ್ನ ಎಕ್ಸ್ಪ್ರೆಸ್ ಮಾಡಕ್ಕೆ ಬಂದ್ರೆ then the set of vectors alpha 1, alpha 2 to alpha n are linearly dependent. Note on the difference there. Alpha 1, alpha 2 to alpha n linearly dependent agidre, any vector alpha k lying between alpha 2 and alpha n can be expressed as the linear combination of the preceding ones. Conversely, converse is also there because we have if and only if. Suppose alpha k is the linear combination of the preceding ones, alpha 1, alpha 2 to alpha k minus 1, ಅದರಲ್ಲಿ linear combination ಅಂದಾಗ c1 alpha 1, c2 alpha 2 ಹೀಗೆ ಬರೆಯೋಕೆ ಬಂದ್ರೆ, then the set of vectors alpha 1, alpha 2 to alpha n are linearly dependent. Let us cite this with an example, otherwise you cannot understand this. Okay, let us check. Any one of these problems, but it takes time. Okay, but you have to work this problem. If possible, I shall work out this in the next class. Okay, next, proof of this. No, I want to give some examples for this. Then only I can give you the proof. Otherwise, you won't understand this theorem. So what I shall do is I shall close at this hour because I don't have the examples before me now to put this on the screen. So what I shall do is I shall conclude this meeting for the time being, and I will take this tomorrow. Do you have any doubts, participants? Do you have any doubts? Suhasini?
No, sir.
Okay, right. I shall conclude this meeting because I should have an example for this theorem, and I will take that in the next class. Thank you.
Thank you, sir.
Okay.